Good morning, students. Here is the second part of the mathematics that we started this week. The topic is circular measures. And the objectives are as follows: to determine the lengths and areas related to circle. Number 2, use circular measure to solve problems. And we will do examples on an arc. Example on arcs, chords, sector, and segments. Then followed by exercises on circular measure. Here we go. I hope all you are set with all your writing materials. Number 1, lengths of arc. What is an arc? It is part of the circumference. This is the minor arc, and the other lower part here is the major arc. You have an angle here, so always make an angle at the center. Call it theta. So the length of that arc is a ratio of this angle over 360, the entire angle of a circle. That is this, times the circumference of a circle. This 2 pi r is circumference of a circle, where L equals to arc length, and theta is the angle at the center, and this is the radius small r. This is the radius from the center of the circle. This is the radius. Example: find the length of an arc of a circle of radius 7, which subtends an angle of 72 degrees at the center of the circle. So this is the diagram. This is the arc. This is the arc we want to look for. This is the radius, 7 cm. Here is 7 cm. This is the center of the circle. We have 72. That's the angle at the center. I want to find, we call this one A, the arc AB. The arc is AB. So we use that formula. The angle, that is this 72 over 360 times 2 pi. Pi is 22 over 7, then times the radius. When you simplify that, you have 8.8 cm. 8.8 cm. That's the length of this arc. Here is 8 AB. Here is 8.8 cm. Second example. Here now we want to look for the angle. We have to look for the angle at the center. Find the angles obtained by an arc of length. This is the arc length here, 13.2 cm. You want to look for the angle. The radius is 7. The radius is 7. So this is the arc. The radius is 21 cm. Here is 21 cm. So we want to get this angle theta. We know here to be 13.2. That's the arc length AB. So we now put this 13.2 as the arc length, then theta over 360 times 2 times 22 over 7, and then times the radius, that's 21. Making theta the subject, we have this. We have 36 degrees. So the angle there is equal to 36 degrees. So that's the angle, 36 degrees. That's the angle at the center. So you do this. This will be assignments or classwork for you. It's taken from New General Mathematics, SS1 on this page, on those pages. Now I now move over to chord. The chord length of chords. This is what we call chord. This straight line. And this is the midpoint of that chord. This one is meeting at 90 degrees. This is the radius, As usual, this is the radius, this is the center. So we want to find the length of this chord AB. AM is half of it. So the formula is 2 pi r theta over 2, because this angle will be divided into 2. That line will bisect the angle. So this is theta over 2. Theta over 2. Using sine ratio, this is the opposite. You know the radius, and you want to find here. It will be sine. Sine of half of this angle will give us this place over r. So when you get this one, then the length we are looking for is 2 of them. So you now multiply this. So you now have the formula as 2 pi r sine theta over 2. So using that formula now, I will give you this example. Find the length of the chord of a circle of radius 6 cm which subtends an angle of 60 degrees. 60 degrees at the center. This is the chord. Let me call it XY. Then this is the center. The radius is 6 cm. Here is the radius. So this angle here is 60. So here will be 30. So here will give us 30 degrees. And here is also 30 degrees. So we want to know this place. This is the midpoint. M. You get here. The ratio of that will be sine. So using that same formula, or you find this one separately and multiply by 2. Then we can just use the formula. 2 times the radius, that's 6. Then sine 60 over 2. And that will be 12. This is 12 times sine 30. Sine 30 is half, that's 0.5. Multiplied by 12, it will be 6. So the whole of this length is 6. As you can see, here is 6. So since this angle is 60, here too will be 60, here will be 60. So it's an equilateral triangle. So all the 3 sides are equal. You can see it's correct. Let's move on to perimeters of sector. This is a sector, the center O, bounded by 2 radii. So how do we get the perimeter? It's going to be this plus this, then plus the length of this arc AB with an angle of theta at the middle. So we already know how to find the length of arc. So we now have it 2r plus arc length, which is theta over 360 times 2 pi r. So that's the perimeter. Now let's do example. So we want to find the perimeter of a sector of a circle radius 14, which subtends an angle of 36 at the center of the circle. Take pi to be 22 over 7. Using the formula, we simply have this. Let me draw the diagram. The angle here is 36. The radius is 14. Here is 14. Then this is the center. This is A and this is B. So this is the radius times 2, which is this. Then we now calculate the arc length. 36 over 360 times 2 times 22 over 7, then times 14. This will be 28 plus 8.8, and the answer will give us 36.8. You can see here is the arc length here is 8.8. You now add it to this 14 plus this 14, and it will give you that same answer. Now, perimeters of segments What is a segment? This is what we call segment, bounded by an arc and a chord. The chord we've done already, both of them. We have an angle of theta at the middle. Theta is, and the formula is simply the length of the chord, which is this, 2 pi r theta sine theta over 2, 2 pi r sine theta over 2, plus arc length, which is theta over 360 times 2 pi r. So let's do this example. Find the perimeter of a minor segment of a circle of radius 7 if the chord sustains angle 60 at the center. So yes, this is the angle at the center, 60 degree. This is A, this is B, this is the chord AB, and this is the center of the circle. So we need this chord as well as this arc. This is the segment. This portion is the segment. So the length of the chord, 2 times the radius, sine 60 over 2, plus 60 over 360 times 2 pi, which will be 2 times 22 over 7, then times 14. Simplifying this one will give us 14 plus 14.67. Adding them together, we have this. So that's the answer. The chord is 14. You can see it's an equilateral triangle again. Here is 14. And this place is 14. Why this one is 14.67 centimeter. So adding these two together give us the same answer. Let's move on to another. So I give you this one as assignments through classwork taken from SS1 on this page, on these pages. So we move on to another aspect. Now we move on to sector. This is what we call a sector. So I've told you before, it's bounded by 2 radii and an arc. This is the arc AB. So this is the minor sector, making an angle of theta at the center. So it's a ratio. Area is a ratio of this angle over 360, the entire angle of a circle, times the area of a circle. That is pi r square. Pi r square. So theta over 360 times pi r square. That's the area of a sector. Example. A sector of 80 degrees is removed from a circle of radius 12. What area of the circle is left? We are interested in the leftover when you remove 80 degrees of that sector. So the remaining one. So the angle that will remain, the entire angle is, the angle we are interested in, theta, will be 360 minus 80 degrees. And that one will be 280 to 80. So we are dealing with the major segment. So this is the major, this is the 80 that has been removed. So we are looking for this arc length here. We are looking for that area rather, sorry. So we use the formula. We've gotten the angle at the center here. The angle here is 280 degrees. So it will be 280 degrees over 360 times 22 over 7, then times 12 square, which is 144. And by the time you simplify that, you have 352 centimeter square. 352 centimeter square. That's the unit of area. Take note of that. Here is 12. Here is 12. It's here. So I move on to now area of segments. Area of segment, we want to find the area of this, the segment. So inside this sector, we have a triangle, an isosceles triangle, and then a segment. So the angle here is theta. This is the radius. This is the radius, center O. So the area of this segment is area of the sector, the entire portion, minus area of this triangle. That's isosceles triangle. You have the formula as theta over 360 times pi r square, then minus half radius square sine theta. So this is the area of that triangle. Now let's take an example. Calculate the area of the segment of the circle of radius 10 cm, which subtends angle 63 at the center of the circle. So what this angle here is 63 degree. The radius is 10. This is the radius, is 10 cm. We want to find the area of this segment. So this is area of the sector, 360, that's 63 over 360 times pi. That is times 22 over 7 times 10 square, which is 100. Then minus area of this triangle. This triangle is half times 10 square, 100, then sine 63 times 63. So when you simplify, you have this 55 minus 44.5. Then doing the subtraction, you have this. So the answer is 10.45 centimeter square. So that's the area of this portion, of this segment. So this is the assignment for you, taken from New General Mathematics, SS1, on pages 154 to 155. We equally have some other assignments on a new further maths project, SS1, on pages 137 to 38. Now I move on to the concluding part of this: surface areas of solids. That's all those solids we have done. We have to look for that of prism, cylinder, cube, cuboid, etc., cone, pyramid, and compound shape. Here we go. This is cylinder. This is the curved surface area here. This area is called the curved surface, here, and it is this. This is the curved surface, and that is the total surface area, the entire, including this area and the area of the bottom. This is a circle, pi r square, then pi r square. So when you add this plus this, it will give me this. Then the curved surface is this. So when you can factorize and get this. So I take example. Example: a closed cylinder container has base radius 7. So the radius here is 7. Height 10. Here is 10. So we are asked to find the area of the two ends. That is this circle and the one at the bottom. So it is 2. The area is 2 times 22 over 7, then times 7 times 7. And that will give us 308 centimeters square. Curved surface, it will be, that's C, here, I'm here. It will be 2 times 22 over 7 times 10, the height, and it will be 440 centimeters square. Now the entire surface now of the cylinder, it will be the addition of these two, and it will give me 748 centimeters square. and move on. We want to look for this an open. The next example is an open box. Measures 8 centimeter by 6 centimeter and by 5 centimeter. Find the outer surface area and then the volume of the box. So since here is open, here will not be part of it to be removed. So we only have the bottom. Here is 8. Here is 6 and the height is 5 cm. So looking for this one will be 6 times 8 times 6 as this. Then this side and this side, there are 2 of them. So it will be 2 times 6 times 5. We have this. We have that. Then the last one, which will be 2, this side and the back. So we have 2 times 8 times 5. And the total is 188 centimeter square. That's the unit of area, centimeter square here. Then the volume is length times breadth times height. That would be 8 times 6 times 5. And the answer is 240. That's the volume. So I give you this one equally as assignment and classwork taken from the same textbook. So I move on to total surface area of cones and pyramid. That surface here. This is the curved surface. The curved surface here is C. So, and it's given as this, pi r L. Why? We know that this is a circle, which is pi r square. So this will now become, the total surface area will now be area of the circle plus the curved surface, which will be pi r square plus pi r L. Factorizing, we have this. So also take note of this. Using Pythagoras theorem, in this right angle triangle, you can find this is the radius. Here, that place is the radius. You make L the subject. Through Pythagoras theorem, you have this formula. Take note of that. We need it. Now here, calculate in terms of pi the total surface area of a cone of base diameter 12. Note here, the diameter is 12 and height 10 cm. So it's given by that. You can see it in the diagram. So we need to look for that height, slant height here. We need it. So here, the radius will now become 12 divided by 2. So R, which is 6. So here is 6. Using Pythagoras theorem here, we now have this. That is 10 square plus 36. 10 square, that is 100. You get this, 10 plus 36. So you give us the square root of that. Square root of 136. So using that formula, we now have this. We now have that. Thus, we have that as the answer in centimeter. So I move on. Another example. A 206-degree sector of a circle of radius 5 is bent to form a cone. Find the base radius and its vertical angle. This is the diagram. This is the diagram. We want to find this radius. This is the base radius. So, you know that the radius of that sector will form the slant height. This is L now. Slant height. So it's a ratio. It's a ratio. You can just use it. The angle, that angle 216 over 360 times the radius. This radius will give us the base radius here, R, and it is 3 centimeter. The second aspect, the vertical angle, using trigonometric ratio, sine. This is the opposite and this is the hypotenuse to be sine. So sine alpha, this alpha, will give us 3 over 5, which is 0.5. Then making alpha the subject, it will give us this angle, 36.8 87 degrees. So the vertical angle is this two. Adding these two together to give us 73.74 degrees. And move on. This is a pyramid. So always, a pyramid always have the slant faces. These are the slant faces. They are always triangle. Here we have, it could be a square base pyramid or a rectangular base pyramid. So the total surface area is the base, that base, plus the area of the triangular faces. So that's that. So here now, we have this example. We're given that pyramid. It's having a square as the base. This is the square. It asks us to look for, it is 8 by 8. So the area is 8 times 8, which is 64. Now they want us to get the slant height of this one. So there's a triangle here. You can bisect it into two. So we want to get this h. Why the height of the real cone is given to be 5.7 centimeter. They want us to get the slant height. So this is the slant height. Here is 8. Here will now become 4. Here is 4. Here is 4 because it's an isosceles triangle. So we now move on. Using Pythagoras theorem, we now have this. Yes, here is 4. So here is 4 in this right angle triangle. Here is 4. While here is 8. This is the height we want to look for. Making h the subject, it will give us this one square, which is 64 minus 4 square, 16. Then that one will be root 48, which will be 4 root 3, which is 6 point this, approximately this. Now we want to look for the area of, there are 4 of them, this triangle, there are 4 of them. So, and we know that, okay, we want to look for the area of this complete triangle. This triangle here, complete. So, and we know it is half base times height, half base times height, half base times height. And this will give us this, and the answer will be 27.71 centimeter square. So the total surface area of that pyramid will be this area plus this area, plus the base area, this area plus the base, which is 64. And that one will give us 174.9 centimeter square. We are asked to, lastly, we want to look for the volume. This is the volume. It's 1/3 base area, which is 64, times the perpendicular height of that pyramid. And that one will give us 121.6 centimeter cube. That's the volume. So I hereby I'm giving you this one as assignment. It's taken from New General Mathematics, SS1. So you do them, and I wish you the best. In case you have any question to ask, you can contact me via my email, the official email, which is at adeoye.matthew. It's at the beginning of this very class. So I wish you the best. Thank you, and have a lovely weekend. God bless you.